Good morning, everyone. I am Alexandre Lucas, Senior Researcher within ESCTech. I'm the Technical Coordinator of InterSTORE. And it's my pleasure to welcome you to the fourth Stakeholders meeting, even though I think it says third on the top, the title. No, Elizabeth, you have to correct this.
Yes.
I see that we have some new elements that we've picked up along the way. So for the newcomers, in InterSTORE, we've used this instrument, the stakeholders group, since the very beginning. It's an advisory. It was initially an advisory board that supported us during the specification, the requirements part of the main tools that we ended up developing. And then we had the second stage where we enlarged the group. And so I'm happy to say that we are, as of now, just over 50 stakeholders from different target groups, from different parts of the spectrum. And at this point, we are no longer interested in the developing or co-developing and to get inputs so that we can incorporate in the future versions. But right now, as we come towards the end of the project, so it will finish at the end of the year, we are much more interested in letting the group know what we've done, our accomplishments, and invite you to further use the tools and how you could incorporate it in your own developments and in your own use cases and in real life, actually. So today, this will be much from a perspective of things that are already done, how we did it, and what we've learned. So I have here in our panel today our colleagues from Sunesis, who were the main developers of the interoperable tool, so the legacy protocol converter, and the IEEE 2030.5 native library, client-server library. And then we have our colleagues from Ulish that will talk about how we used these tools in the use cases, the architectures, different architectures that we've tried out, and lessons learned. And then we have our colleagues from engineering who will explain what was accomplished in terms of the developments with regards to the data space connector, which was built upon the OneNet connector. Sometimes we refer to it now as InterSTORE connector, and it will have its own life afterwards, as it is having right now as we speak. Then I invite you to have with us an open mic session. I think it's the opportunity to hear from you how if you think if you expect to incorporate this in future European projects or go towards the adoption to real life cases, in what types of equipments, and also if you think further developments could be done in the tools developed. And we invite you to take part of these future developments in the correct framework that I will disclose at the end. So the main tools for those who are new, and also to remind all of the colleagues, what we've accomplished so far in the project have been the following bullets that you see here. So the first one, as you know, as you remember, we are using the IEEE 2030.5 standard. You can think of it as a dictionary, and we've applied it to legacy systems that did not work with the IEEE 2030.5 format. So we've developed a legacy protocol converter, but instead of using the original version of the IEEE 2030.5 that was using REST APIs, we are using a NATS communication, incredibly fast. And it's this mixture of the IEEE 2030.5 and the NATS that makes the developments here in InterSTORE very powerful. Then we have also for the native speaking IEEE 2030.5 for the assets themselves, for them to be able to communicate with the NATs, this NATs communication, we've developed a library, client-server library, to enable this communication. Then we have developed also a set of testing procedures. Our colleagues from RWTH were responsible for this. We've developed a storage sizing hybridization tool. So for batteries, because this was one of the main focuses of the project, to consider distributed energy resources, and we use the case for distributed storage. We have the user interface for the data space connector. We have developed 4 data space valorization cases, and all of this is open source. I'm sorry. Regarding some numbers, the work that we've accomplished only this year, only 2025, regarding dissemination and communication, I'm quite happy to say that we've attended so far, and we are still in September, 8 fairs, 15 conferences, policy-related events, 4 events, and other types of events, just 1. And we've accomplished more than a dozen publications. So I think in terms of this aspect, it has been also quite successful. At this point, in terms of versions of the software, we are at version 1.5 of the legacy protocol converter, which is just this weekend, Matthias, wasn't it? The new version. As for the user interface for the data space protocol in InterSTORE, we have the 1.3.2 version. This will have further developments in other European projects. I understand that even the data space protocol compliant version has been released in the Twin EU project. And since our last meeting, we've had our demos fully running. I'm also happy to say that all except one is still running. And not only have we been able to monitor successfully several different types of variables using the interoperable toolkit, but also control. It's not just a question of monitoring, we're controlling. We've used both the legacy protocol converter and the native libraries, both at the energy management system level, but also at the device level. Have we deployed these tools? And we've also had the support from our colleagues from Spain, HESTEC, in the performance studies under lab environment using the real-time digital simulator. As I was saying, our tools have been released open source, and you can find them both in GitHub and Docker Hub. Since we don't have much visibility in GitHub, I can give you some numbers, and quite successful numbers given the state of maturity of the releases. Only Docker Hub itself, we have more than 1,000 legacy protocol converter downloads, so just 1,100. Regarding the DSO connector, more than 400 downloads, also for the local API service, 150. So it's looking good. And if you consider that GitHub in some sectors has higher visibility, so if we add them up to these numbers right here, these tools are having quite visibility. In terms of just to highlight some main performance indicators, which I think they're quite sound. I was referring before to the communication, the NATS communication over the IEEE 2030.5. We've reached under 100 milliseconds. Actually, our colleagues in Spain reached approximately 50 milliseconds. So it's quite, you can see it's quite powerful. It unleashes many use cases, critical services, given the speed and given the fact that the NATS is an asynchronous way of communication. And it enables many-to-many communications, as we will highlight further along the presentation. And we've used this in different architectures, as I said, and different platforms and devices. So the number of different TERS devices successfully tested and demonstrated, 32. 37, if we consider the number of assets monitored by the energy management solutions themselves, 21 as the number of different DERs devices and M successfully tested with this IEEE 2030.5 in our real pilots. And we are talking about, in terms of battery capacity, we're not talking about little powers. It's just already over 4 megawatts. So it's not a negligible thing. We are using already quite sound equipment and installed power. We were also able to put out our white paper, which I invite you to have a look, especially for the colleagues who are getting in touch for the first time with the IEEE 2030.5 and the NATS communication, and to be aware of what use cases it can unleash, what is the potential, but also how it compares to other standards and protocols. What are the current developments? So far, we are converting from Modbus and MQTT to IEEE 2030.5. And also we provide some recommendations towards adoption, but also towards policy recommendations. So if you simply scan here our QR code, you can download the white paper, but also if you just simply go to our web page, the InterSTORE project, you will find all the resources, not only the white paper, but the links to GitHub, Docker Hub, and so on, and social platforms. Now, I'm very, very happy to say, because I was just this past week at the Linux Foundation for Energy Summit. Maybe I see some colleagues that were there connected. And I'm happy to say that InterSTORE is now, yes, we will be able to share the presentation. I'm happy to say that the InterSTORE project is now a Linux Foundation for Energy project. We've registered the developments under the name Cupid. Cupid stands for Controllable Unit. We have to see the acronym, but it's a new name. And this is important because this is where the future stage of the developments will be. You have here the URL that you can follow. So the project is already there, the Cupid GitHub page. And because InterSTORE will finish at the end of the year, we need a stage to continue. And this is why we invite everyone from the stakeholders group. This is where it makes sense first to address. Of course, we've disseminated this at the Linux Foundation for Energy Summit, but you guys were first adopters. You are receiving the news and the versions firsthand, and so you have an opportunity here that others don't have. So please, I invite you to go and to follow and to commit your future developments. Not only you can engage with the Cupid project and share your own developments, who knows, another conversion with a legacy protocol converter or something else that you find pertinent, but also since we have so many members from industry, we are looking for adoption. And there is no reason why not adopting it or finding limitations in the use cases that you want to pursue? Because this solves it was a constraint, the speed before, but not anymore. So we are looking towards, and we invite you towards adoption, real life adoption, but also simply to propose these developments, which are again open source in other European projects. You can use it yourselves and further develop them there. Also, we invite you to engage with InterSTORE partners for knowledge transfer. We were engaged with three stakeholders recently, and they had their own developments, their own implementation. They were learning new things, and they were sharing with us. So this is what the community does, and this is why we want to incentivize community engagement, to learn from each other. So in the end, it's to share experience of your own projects and implementation. And as I said before, work still needs to be done, and that's why we need you as a community. Invite you to the stakeholders group in Cupid project. Also, since I'm inviting you for so many things, last but not least, just to let you know that we will have our final event on the 25th of November in Brussels. This is the venue address. Good news also for those who cannot make it locally is that this is a hybrid event. And so you just need to go to our webpage. You have there the registration link for the InterSTORE final event. It's very easy, takes just a few seconds, and we will put you in the list so that you can follow this very happy and a milestone, a true milestone of the project, which is the final event. Okay, without further ado, I will pass the floor now to our colleagues from Sunesis. Matthias, please, Matthias, take the floor. Thank you.
Thank you very much, Alex. I would like to briefly explain what's new in the legacy protocol converter, demonstrate how the legacy protocol converter can be configured with a simple UI tool that we have also developed, and say some more things about the legacy protocol converter. But before I go to what's new, let me just briefly summarize. So the legacy protocol converter, or the legacy systems protocol converter, it's a software component. This software component has been designed to efficiently transform several protocols among each other. Currently supported are Modbus, MQTT, RabbitMQ, and of course NUTS. And NUTS is basically the main transport protocol for the IEEE 2030.5 representation of messages. We also support IEEE 2030.5 in XML format, which is the original as specified by the standard. And also the JSON representation. So JSON representation is basically a mirror representation to XML. It has the same tags, element names, and so on. It only uses the JSON, which is, well, modern, more commonly used, and so on. Now we have designed and developed the legacy system protocol converter with special attention that it is a lightweight microservice based component, which can on one hand be run on basically any hardware, from Raspberry Pi and IoT Max devices and other embedded devices, which are relatively low power and so on. But still, the legacy system protocol converter can be run there efficiently, and we have demonstrated and proven this in the InterSTORE project, where various partners have tried that out. So to servers, which could be relatively simple servers running this on hardware, on virtual machines, or they can be heavyweight backend servers running Docker or Kubernetes. We have also put a lot of effort on horizontal scalability, which means that there can be many instances of the legacy system protocol converter running in parallel, and they will load balance, so they will distribute the load, which provides efficient execution on one hand, and it's also high availability, which means that if one legacy protocol converter fails, the other instances can take over the work. What is basically supported are the different transformations between STAT, Modbus, MQTT, NAT protocol, where you can use different representations. And if we go to the next slide, please. This figure tries to demonstrate this. You can see on the left side several devices. The first one is using Modbus and the legacy protocol converter, which converts the messages to IEEE 2030.5, stores this in the NAT's messaging cloud, and forwards this to the EMS side, which is on the right hand side of the slide, either in native format or in some custom formats such as MQTT or RabbitMQ, which has also lately been supported. Then we have some native devices on the left side and some MQTT devices on the left side. So basically the message here is that we can mix the protocols, convert Modbus to IEEE 2030.5 and back, convert MQTT to IEEE 2030.5 and back. We can even convert Modbus to MQTT or MQTT to Modbus. So all the possible combinations are supported. Now security is also handled on the NATS side. The security is handled in such a way that all the devices and EMS systems and the legacy protocol converter itself require authorization and authentication to access the NATS messaging cloud. This can be achieved in different ways, in a simple way with username and password, or in a more complicated way with digital certificates or JWT tokens, with future possible support for some even more advanced security or authentication and authorization measures such as Kerberos tokens. All the communication over the wire is also encrypted, so we always use SSL or TLS, this means transport layer security, so that no data is so all the data is encrypted, nothing is sent in plain text in such a way that it could be easily intercepted by somebody. So basically, to use the legacy protocol converter, there are several options how to proceed. The easiest way would be to use the pre-built Docker containers, and we have published them on the Docker Hub, which I will show a little later. And it's really simple for an IT person. You have to pull the Docker container and basically run it. But of course, before you can run it, you also have to configure the transformations. You have to configure, for example, how the Modbus or MQTT messages will be transformed into IEEE 2030.5 and back. And I will show you how you can do this with the UI that we have prepared, which is a simpler way than writing a configuration file. But before I do that, let me just explain the other options. So instead of using the pre-built Docker container, you can also go to the GitHub. and use the source code directly to build the legacy protocol converter or include it into your products. We have published this under the MIT license, which has very little limitations regarding how you can use this software. You can basically use it, modify it, integrate it with your software without any licensing or any other legal constraints. If we go to the next slide, please. This slide shows how the configuration of the legacy protocol converter has to be done. On the left hand, here in the black box, you can see an example of the MQTT message in JSON format. On the right hand, in the black box, you can see the IEEE 2030.5 in the XML format. And this is just an example. We could have other formats or other structures on one and the other hand. But the basic idea is that you define a configuration file where you define the configuration. So this transformation file might look a little bit complex. It is very well documented. If you will look at the GitHub into documentation, you will see that it's very well documented. But you basically have to provide some instructions how the different fields are mapped from the source structure to the destination structure and back. To simplify this, we have developed a UI. And if we go to the next slide, please. This UI is published on a website, sunesis.si interstore/LPC. I would just briefly show you how you can proceed. And if you agree, I will share my screen now. Can you see my screen?
Still loading? Yes.
Yes.
Okay. So if you go to this sunesis.si interstore/LPC site, you will see a simple user interface where you can create a new LPC configuration here in the bottom right side, or upload some existing configuration. I will just briefly walk you through the creation of an LPC configuration. It is basically, there are basically 3 steps which are necessary. First, you have to specify the connections, then you have to specify the transformation, and finally, and the optional step is the registration. So if a device needs a registration or something like that, this is also supported. So what I will do, I will basically specify a NAT connection. You have to specify a name, a type of the connection. You can see NATs, MQTT Rabbit, MQ, Modbus Serial, Modbus TCP. In most cases, you will need 2 connections. One will be a NATs connection. You specify a host where your NATs server is running, the port, the username, the password for the connection, and the reconnection strategy. So you will basically, in most cases, need 2 connections, and the other connection would in this case be, for example, an MQTT connection, where we again have to specify some parameters such as SSL connection, again, username, password. Of course, you can change those values later on. These are just for the demonstration. Also the version of the MQTT. And then you can continue to the mappings. And here on the mapping side, you would specify the name of the mapping, some short description, for example, sample mapping from MQTT JSON to IEEE 2030.5 NATs. and then you would specify the incoming connection would be the MQTT, which would be the demo MQTT that we have defined on the previous screen. The outgoing connection would be NATS, and we would use the demo NATS connection that we have also specified in the previous screen. And then you go to the actual mapping and would say that the outgoing format would be JSON or XML. You can select here. Here we have some technical parameters such as retry count for scenarios where you would like to retry the sending of the message if the connection would fail, if you have like a bad internet connection or something like that. And then you specify the topic names and the message structure itself. Now, this user interface allows you to browse the IEEE 2030.5 elements. So once you click on the message path, you get here a list of all 321 IEEE 2030.5 elements. Of course, I don't have the time now to go into the detail, but for example, if you would like to use the event structure, you would basically click on it, and this UI would already fill the event structure. And now all you have with some sample data, and now all you have to do would be to specify how these values are mapped from the original message. And for this, you would insert the LPC mapping structure and specify the path from the original source message. You would also specify the data type, some pattern, and some other values. This becomes now a little more technical, but this way you would specify the mapping. And that's basically what you need to do. So this would be one-way communication or transformation from MQTT to NATS. And then you have another section here where you can, in the same way, specify the mapping from MQTT to NATS or vice versa in the other direction. And some additional features which we have found out at the consortium that are required, such as interval requests or device registration, which is also optional. So this means that the device would register itself first. And once you are ready, you simply download the configuration file. And this configuration file looks like this. So it has a version, it specifies some connections. So this is then basically the source code of the configuration, which might look a little complex, but it's quite easily readable by IT people, and almost everybody who is familiar with MQTT, JSON, and XML will know what to do. Here is the definition of the structure of the messages. And what you basically need to do is to save this configuration file and use it once you run either the Docker container or the legacy protocol converter if you build it yourself from the source code. So that's basically it. To get more information, I would like to invite you to go to the GitHub. As Alex already mentioned, the legacy protocol converter can be found on the original Horizon Europe InterSTORE repository. Or even better, it can be found on the Linux Foundation Qpid project repository. Both repositories are mirrored. That means that there is the same code on both. And what you can see here is quite extensive documentation, which explains all the different possibilities with the configuration, transformations, logging, setting up the connections, securing the connections, and so on. And of course, I don't want to go into too many details. Let me just mention that we have started to collect the configuration examples also. And you can find here some specific configuration examples from the InterSTORE projects, which have been used in real world in practice. And you can have a look how this has been configured, which can help and simplify the testing and the deployment. You can also look at the releases. As mentioned, we are currently in version 1.5, and you can also see the log of all the changes for all different versions. There have been some interesting and important changes, such as Rabbit MQ support with custom mapping of topics and queues, several performance improvements, automatic time synchronization between the devices and the legacy protocol converter. Then implementation of different different Modbus libraries, because we have figured out that not all Modbus libraries work with all the devices and so on. So basically, as mentioned, this is the repository, of course, all the source code and the MIT license, as mentioned. And let me just show you also the Docker Hub repository with several Docker images. Let me click on the legacy protocol converter. And here you also have the instructions and some information on how to use the Docker image. So it's pretty straightforward. So that would be all from my side for the moment. And I would hand over to Daniele from Jülich to explain the use cases. Thank you very much.
Thank you, Matthias. Elisabetta, I think you're going to share the presentation, right?
Yes, it will take a couple of minutes.
Okay, no problem. So in the meantime, maybe I can break the ice, introducing myself. So thank you everybody for joining. I'm Daniele Carta from Forschungszentrum Jülich. In the context of this project, we were responsible for work package 5. There is the work package focusing on the pilot demonstration. And this is why today I'm going to give you a little taste of the use cases and the different architectures that we have been using in the pilot site. Just 1 second, then I'm taking control. Okay, perfect. So in InterSTORE we have 5 pilot sites. In particular, we have one in Austria, Italy, Germany, and Portugal, plus the 5th in Spain is a laboratory testbed, but we consider it a pilot site anyway due to the kind of activities that were being carried out there. And as you will see during this presentation, each pilot focused on some very specific aspects related to the hybridization of distributed energy resources. In this slide, you can see an overview of the different use cases that we had. In particular, we had 9 use cases, typically 2 use cases per each pilot. And as you can see by the columns, the pilots were focusing on different aspects, as I said. So hybrid energy system performances, in some cases, the monetization was explored, and so on and so forth. But I will go more in detail during the presentation. So let's start with the Austrian pilot. Here we had 2 use cases. Use case 1, DES flexibility market monetization, and use case 2, energy community DES utilization. Here, as you can imagine by the names, the focus is on local energy communities, and in particular here the partner implemented the InterSTORE development in the context of a local energy community in Austria, in order to provide, let's say, services and maximize the benefits associated to an optimal energy usage within the community. This was particularly important because in Austria there are specific, let's say, legislations that allows community users to pay basically lower taxes depending on the energy usage. So here was particularly important the activity carried out by the partner in the project. So we had both monitoring controls made by means of the legacy protocol converter. In this case, we had inverters from various manufacturers. As you can imagine, being a local energy community with different households and different assets, each household had inverters and components by different manufacturers. So this was definitely a challenge in the pilot. And also, given the nature of the community itself, we had the communication made via cellular network. Here you can see an overview of the architecture in this pilot, and in particular, okay, perfect. You can also see my pointer. So from a hardware point of view, here there is a representation of one inverter that was connected to the home router, okay, and then in the same network there was a IoT Max device, which was then connected to the energy management system provided by the partner CyberGrid. So in particular, in this case, the energy management system was CyberNOC, and here there was a VPN tunnel to secure the communication directly with the energy management system and the household, so the local network. When it comes to the software part, as you can see here, Modbus TCP is mentioned as a means of communication between the inverters and the LPC. This is because Modbus is the protocol that is mostly used by the hardwares inside the local energy community, and the legacy protocol converter, as also mentioned before by Matthias, in this specific case was deployed on the IoT Max device. So also, as shown here in the slide, the final communication between the IoT Max device and the energy management system was made via IEEE 2030.5. So here, as I mentioned, since again we are in the context of a local energy communities, there are inverters from various manufacturers for both the battery energy systems and the PVs. Here you can see an example of the manufacturers and the models that were integrated in the context of the pilot. Just a small comment, the majority of the inverters were from Fronius, which according to the partner were also the most reliable and stable when it came to the communication and the integration in the CyberNOC platform. Okay, now it's time for the German pilot. Here in Germany we had 2 use cases. Use case 3, grid supporting BSS, and use case 8, multi-physics flexibility optimization for home management systems and their global integration, very long name. So here we focus on the integration not only of battery systems in our energy management platform that is based on Fiverr, but we also looked on how we can integrate this multi-physics flexibility, particularly given by the heat pumps and their thermal storage in the context of, let's say, a global energy system optimization. So here the key aspects are the multi-physics systems. Also in this case, we had monitoring control by means of the legacy protocol converter. We implemented the LPC on a low-cost device, in particular on a Raspberry Pi. I will show some results later. And we also studied the deployment times needed by different users to, let's say, prepare the configuration files that Matthias presented before. Here you can see a overview of the architecture. So we have on the DR side the various assets that were integrated. We have 2 battery systems, a large PV field, and a heat pump with its thermal storage. As mentioned here, the LPC was deployed on a Raspberry Pi using Docker containers. And so, given the nature of the different protocols that were involved, we had on one side, so on the DR side, the conversion from Modbus and MQTT into IEEE 2030.5, creating this interoperability layer underlining here with the purple black background. And then we had a second transformation because in use case 3, we use the fireware-based ICT platform of the campus that communicates via MQTT. Sorry, there is a typo here in the slide. And in use case 8, the Eton EMS was actually communicating with the Modbus. So yeah, here I inverted, sorry, the two. But the key concept is we had these two transformations running on the Raspberry Pi. So as I said, one of the key aspects in this pilot was to show the time that is needed for the integration of the assets using the legacy protocol converter and comparing this time with the time that would be needed by a random user for the implementation via the, let's say, traditional integration, in this case, the fireware integration. And here you see by rows the different users that were involved. We had some software developers, but also PhD students and postdocs. While by columns, you see that the organization based on different assets. And here, I don't want to spend too much time on this table, but the key concept is that on average, the integration that was needed, the time that was needed for the integration with the legacy protocol converter was 86% faster than what was needed with the, let's say, traditional fireware solution. And in particular, here you will see that 50 hours were needed by PhDs and postdocs, but here, after 50 hours, we simply decided to stop continuing with the demonstration because it was already taking too much time. So when you see 50 here, it doesn't mean that the integration was complete. While, for example, by using the legacy protocol converter and the tool that Mattia showed before, so this user interface on the website, with just 3 to 10 hours, also not expert IT colleagues were able to integrate these assets into this, let's say, energy management system context. Another interesting aspect was the possibilities that we had with the architecture, because since we had the double transformation, as I mentioned before, we could have had many configurations. So a solution one with the transformation on a dedicated Raspberry Pi, but also combination of the two. So in solution 2, you see NAT server and transformation 1 on one Raspberry Pi, and then the second transformation on another Raspberry Pi. But instead, we went directly for a solution number 3, that is NAT server and all transformation running on the same Raspberry Pi. This was no problem at all. So the Raspberry Pi, even though it's a low-cost device, was able to manage all these transformation and the various configuration files. And in fact, as you can see here, I report the resource usage by the LPC. So when it comes to the LPC itself, always less than 25% of the resources were used by this Docker, considering, again, the two transformation and all the configuration files, while the NAT server, also running as a Docker container, was requiring less than 0.2% of the resources. Okay, now we move to Italy. In particular, the Italian pilot that was in Rome. Here we had one use case 9, management of EV charging clusters and hybrid electric storage systems. Here the key aspects are the test of local ancillary services for the distribution system operator, the inclusion of EV chargers, batteries, supercap, and PV system. Also in this case, we had monitoring control. And particularly important, this is the only pilot where we had the chance to test the integration of a native of a device that was natively speaking IEEE 2030.5. This is particularly important because in the context of the project, it was difficult to have IEEE 2030.5 native devices already in the field, so simply because currently it's not a protocol that is largely spread in Europe, but here we had the chance to test also this solution. Here there is an overview of the architecture. It's as you can see now, the architecture are getting more and more, let's say, similar. But here the key aspect is that, first of all, the middleware was running on a cloud that was hosted externally by the partner, and in particular, the LPC, the LPC container was running on a dedicated server, and then let's say it was communicating with the application and services interfaces that are used by the let's say DSO to manage the resources and provide services to the network. An interesting aspect of the architecture here in Rome is that the devices were connected in a private network for security reasons. And even though, let's say, there was this spread of devices and there were some challenges associated again to security, firewalls, LANs, and so on and so forth, the partner was able anyway to perform the demonstration integrating, again, these devices, even though they were in different, let's say, sub-networks. Now we move to the Portuguese pilot. Here we had two use cases. Use case 5, hybrid storage, higher performance and flexibility provision, and use case 6, which is management of battery system for node capacity increase and user DR. Here, the key aspects are for sure the EV driver engagement. In particular, here the partner was able to engage with EV drivers or users that were not directly involved in the project as partners, but these were normal EV drivers that were using the charging stations in the location of the pilot. We had also hybrid energy battery systems, monitoring via the legacy protocol converter, and control via LabVIEW. Here is an example of use case 5. In particular, here we had two types of batteries. One is a vanadium redox flow, and the other one was a second life lithium battery. As I mentioned here, the monitoring was made via the legacy protocol converter, while the control was performed using a LabVIEW software. But as I mentioned before, particularly important here is use case 6, where there was an engagement of the EV drivers. And in particular, as you can see here, there was an evaluation. Sorry, I think there is some background noise, so I will ask. Okay, perfect. Now it's fine. Thank you. So here, as you can see, there was an evaluation on the amount of CO2 emissions through the day, and this information were shared with EV drivers in order to promote the charging of the vehicles in period of times with lower CO2 emission. And here I report an example of a heat map that shows the behavior change of one EV drivers due to the let's say, first of all, information that was provided by the partner, and also the incentives that were provided as well, because let's say also incentives play their role in changing EV drivers' behavior. Last but not least, we have the Spanish pilot, and in particular, this was a laboratory environment. Again, we had two use cases here. Use case 4, innovative frequency services, and use case 7, adaptive battery energy storage system management for autonomous grid operation. Here, the key aspects are the fast frequency service, because again, we're this partner has this lab facility. It collaborates a lot with the transmission system operator, and they perform many studies related to these fast frequency services, such as even Black Start and the like. So again, looking at autonomous gate operation, and here there was an analysis of the legacy protocol converter response time, and this is, for example, the pilot in which the partner were able to push the legacy protocol converter to the limits and see how it can perform for very fast services. And we had monitoring control made by means of the legacy protocol converter. Here, the architecture doesn't involve any cloud or cellular communication because everything was inside the lab environment. Nevertheless, the legacy protocol converter was implemented in a dedicated server, and the communication was made between the various assets in the lab and the energy management system of this pilot, again, in Spain. Here there is a screenshot of one of the activities conducted by the pilot, where basically there was a fault was simulated in the network, and after a synchronization period, there was a reconnection of the assets, and this is one of those tests where the pilot was able to really push the legacy protocol converter to its limit to see how it can handle a quick and fast communication between the assets and the energy management system that was somehow coordinating this reconnection. So, thank you very much for your attention during this quick overview, but I hope that at least I was able to give you some hints of the characteristic of the different pilots, so that eventually you can pose questions or contact us later on if you have curiosities. And another thing that I would like to mention here is that also, as mentioned by Matthias before, in the Git repository, you will find the config files that have been used by the pilots for that integration. So as an example, if you use, if you have in your system a, I don't know, Bianitsa power quality meter and you want to integrate it using a legacy protocol converter, you have a config file that is already made in the Git repository. Same also for other assets. Okay, now I will leave the floor to myself again for a second presentation where I will simply introduce some lessons learned during these demonstrations in the pilots. So first, when it comes to the LPC deployment, first of all, we do not have to fear the problem of computational burden associated to this solution, because as was demonstrated in the pilots, the legacy protocol converter can be deployed on a low-cost device. We saw the example of the Raspberry Pi, and the resource usage is very low. So even though we are using a board that costs less than 100 euros, let's say there is still plenty of space for computational power. During the demonstrations, we noticed that it's really important to properly define the logging level. In fact, due to the nature of the transformation, the log files, if you want to keep track of all the logs and all the messages that are exchanged, the log file can get pretty big. We're talking about, for example, 4 GB in less than an hour in the case of the German pilot, for example. Nevertheless, this is just a problem that you can have during the first debug phase, because thanks to the proper logging settings, you can avoid these problems. So now, for example, the log files that before were taking 4 GB in 1 hour barely reach a couple of hundred megabytes in 1 week in the same condition. So again, the logging rules really change everything. Config files can be created quickly, and so and this was proved in the pilots also by testing the integration, by having, not expert not IT expert colleagues performing this integration. And especially, I want to underline here that the LPC, let's say, config file creator provided in the website, it's a really good way to start when you don't know how to approach the configuration files at the very beginning. Then once you know how things are done, it's pretty easy also to work directly on the config file. Another nice feature is that the config files can be updated and added while the LPC is running. This means that when you build your Docker container and you run it, you specify a folder where, let's say, the container should read the various config file for the integration, meaning that, I mean, this is, read continuously, okay, and continuously updated, meaning that if you find, for example, that there was an issue in your config file or you want to change something last moment, you don't have to stop all the containers and stop all the communications, but simply you act on the specific config file that you want to edit on the go, and yeah, this facilitates a lot, let's say, the live bug fix, etc. When it comes to the assets integration, in the pilots demonstration, we showed a full integration of Modbus and MQTT-based devices. Here it's important to underline that in some cases, especially with the Modbus devices, you need to be careful with the Modbus library that you use. For example, we noticed that some Modbus libraries were not performing well when using the when trying to control the assets. Nevertheless, this is documented in the Git repository, and so you will find all the information there. We also included in one of the latest release of the legacy protocol converter the possibility to synchronize the exchange of data with an external NTP server, which is a really nice feature. And we proved that this legacy protocol converter is suitable for both monitoring and control. Again, certain assets can be controlled only with a specific library, as mentioned before, and we also saw that we can go up to 100 milliseconds when it comes to the frequency of data exchange with the assets and the legacy protocol converter. Then, thanks to the variety of use cases and assets that we integrated, we showed how this legacy protocol converter is basically manufacturer agnostic. So we tested it with different inverters from different manufacturers, from different purposes like PVs, battery systems, EV charging stations, and also in a multi-physics context. Of course, heat pumps and the thermal storage were not directly defined in the IEEE 2030.5 structure, so we needed an adaptation. We treated the thermal storage as if it was a battery system, basically, but this did not prevent the demonstration to be successful. And then user engagement. So we noticed that there were some challenges during the deployment, especially within the households, because of course, first of all, household owners were a bit concerned about this solution being integrated inside their private house. Some, for example, was scared about the eventual danger for the batteries, etc. But as underlined by the Austrian partners, communication was the key. So they had a continuous communication with all the, let's say, people inside the energy community, explaining them what was involved in the integration of the legacy protocol converter and also in the demonstration phase. And once they were properly explained with all the aspects related to the demonstration phase, people were typically more, let's say, less concerned about their assets. And that's why also in the end, the demonstration in the Austrian pilot was successful. Another important thing to mention when it comes to user engagement is the results from the Portuguese pilot, where more EV drivers would have liked to join and to participate in the demonstration phase, but unfortunately it was simply not possible because of the limited amount of charging stations available on site. This was very interesting when it comes to the demonstration phase, because originally there were more charging stations that EV drivers willing to participate in the demonstration. But then, let's say, thanks also to the, again, the communication, the shared of information that the partners had with the EV drivers in the context of the pilot side, even more users were willing to take a role in the demonstration phase. Okay, so thank you very much again for listening also to this second presentation. And now I will leave the floor to Marc Antonio.
Thanks, Daniele, and good morning, everyone, again. My name is Marc Antonio Lafranca, and I'm working at Engineering Informatica as Technical Manager. Today, we will present the data space framework and connector. So, in particular, to the agenda include the development timeline to show the project has progressed over time. Then we go through the latest main feature and innovation that has been introduced in InterSTORE. We'll take a closer look at specific improvement, including the push mechanism flow, the NATS integration. And after that, we will see some future roadmap for the data space framework. And finally, we will go with the live demo of the latest version to show the current state of the framework in action. This is the timeline and provide a recap of all the development activities related to the data space framework on InterSTORE project. We started with month 1 of the project in 2023 with a solid foundation. We start with the OneNet connector in particular, which itself originated from engineering, general purpose, and agnostic true connector. This framework then was announced in OneNet project with the energy domain specification, integration of the fireware context broker, and also the DSA components. In the March 2024, we developed and released the new open source advanced graphical user interface, along with the blockchain-based notarization service as part of the version 1.0 of the framework. Then in month 22, October 2024, we completed the task focused on data exchange optimization and released the outcome in version 1.1. The development of new push flow mechanism was completed in December 2024. And finally, in month 27, the latest release, we integrated the support for the IEEE 2030.5 protocol using NATS into the energy data space. So start with this block diagram architecture, in which we can see the latest version with all the components released of the data space framework. We have the graphical user interface module in the left of this diagram, with the blockchain module at the top center, with the link with the transaction authorization service. The data transfer optimization is related to the local API module. In the bottom right, we can see the push service to integrate external service via REST API call. And finally, in the bottom left, we can see the NATS client to communicate with the IEEE standard. Start to speak about the push flow scenario. We can start with the question. Why it can be useful provided this new mechanism in the energy data space connector? The response is pretty simple because the standard flow in a data space that involve provider and consumer is quite effective for most scenario, but it lacks flexibility for use cases where data needed to be uploaded and sent in efficiently and near real time. The push mechanism addresses this limitation of the data space by offering easy integration of external API services, near real-time data delivery, ensuring instant access to the data as it is generated. Reduce a bit the latency, and enhance the resource utilization, support for event-driven use cases, ideal for example, for applications that require the immediate data actions, and empower stakeholder to make timely and informed decisions based on the most current data. Let's look to expected flow in a push mechanism. As in the left side, we can see the service provider, and in the right side, the data provider. In the middle, the energy data space connector. The first action in this case is to create the data offering, the service creation and configuration. So in this case, a REST web service is defined according to a predefined interface, and the specified URL of the service is to be defined to it's callable by the push service in the second phase. The data provider can subscribe to this data offering, and once the request is accepted by the service provider, it can push data using the connector in a classic standard way. The step 3 it's the most important step of the push flow mechanism. During the upload process, the web service specified in the configuration as step 1 is invoked in a synchronous way, passing the data entity, both the content file and also, of course, the metadata. This ensures that the data is immediately made available to the service provider environment, outside, of course, of the connector system. As a fourth step, with the completion of the loading process, a technical response returned to the data provider, confirming successful data loading, or in case of failure, providing an error and message code. In this simple flow diagram, we can see the first step done by the service provider that can create a new data push service. Step 2, the data provider will see a provided data into it. So should create a new subscription by choosing a push service from the service list. As step 3 of this flow, the service provider can view a request list of subscription and accept the subscription received. As step 4, data provider can select the push type service so that they can load the data into that. As part of the process, the external REST endpoint is also called, and then a response is returned, OK or failed in case of any problem. In the step 5, as the service provider receives automatically and in real time the data uploaded by the data provider using the exposed REST API service. And of course, can be used the graphical user interface or the API to access to a list of the consumable data and manually on demand download the data file. The second nice feature discussed today is the integration of NATS protocol and of course of the IEEE 2030.5 in the data space. This integration open up significant opportunities to drive the digital transformation of the energy sector and also improve the incorporation of distributed energy resource. The main benefits could be, in this case, enhanced the interoperability, their optimization with the efficient management and utilization of distributed energy resources, data-driven decision-making, insight for grid operator, utilities, and stakeholders, privacy and security management that ensure compliance with data sovereignty and protection standards. Another key benefits is integration with the smart city and the IoT device. And last but not least, improved customer engagement because this integration empower users with insight to optimize energy consumption. This integration brings a host of practical application that can be transform the energy management. For instance, it could be support, for example, microgrid management. Also in the area of electrical vehicle, it could facilitate smoother communication between electrical vehicle charging station, the grid, and more efficient charging solution, and so. Additionally, it can empower dynamic pricing and demand response programs, allowing utilities and grid operator to adjust energy price and manage consumption based on near real-time demand. Integrating the data space with this standard is easy by leveraging a combination of advanced technologies. At the core of this integration is, of course, the standard IEEE. To message transform and bridge the gap between older device system and the new message interface, we can use the legacy protocol converter. To efficient communication between the components can be handled by the NATS server, the NATS protocol, and high-performance message system. And finally, of course, we can use the InterSTORE Energy Data Space Open Framework to provide an environment for secure and scalable data sharing. In this diagram, we can see the preview component. One or more device that using a protocol supported by the legacy protocol converter, the legacy protocol converter module, a NAT server that serves as pub/sub message broker, an instance of energy data space connector, in particular the data space ingestion service. We subscribe to relevant NATS topic, and when the data, for example, telemetry or smart meter or EV charger data is published, the data space will receive it in real time within a specified and defined service. Of course, more service can be defined and mapped to the specific NATS topics. Of course, we have also one or more data consumer, for example, grid operators, standard consumer, or third-party services. So the roadmap regarding the Open Data Space Framework. We are currently working on the submission under the Linux Foundation Energy. We are also building technical communities to support the ongoing development and maintenance. Technically, we are focusing on achieving interoperability, both from a technical and semantic perspective. And this includes the main important feature, the implementation of the data space protocol, which is in beta release in a TwinEU project, as Alexander said previously. We are also working on extending the vocabularies and the standard data models to better support use cases in the energy domain and beyond. Another important goal is to enable near real-time communication, which will be supported through additional protocols and mechanisms. And looking ahead, we are actively exploring digital twin federation, the exchange of digital twin models, and to build a dedicated data space for digital twin interoperability. All of this contributes to the broader vision of the common European energy data space, where we aim to ensure full compatibility. We are planning to integrate with other data space technology, such as EDI, AIDA, and Simple. So the previous slide concluded the theoretical part of this presentation. Now we can start with a live demo of the latest version. And in particular, we will see the graphical user interface. We use the graphical interface to present the data space connector features. We will see the push flow mechanism. And in the final part, we can see the NATS protocol integration. I have to share my screen to present live demo. So okay, can you see my screen?
Yes.
Okay. In this page, we can see the GitHub repository of the Energy Data Space Connector. From this repository, you can get the project and the configuration to start a new installation and configuration of a data space framework. Then we will use two test users to simulate the data exchange. We will use user test 1 as a data provider in this case, and the user test 2 as a data consumer. So I log in to the data space framework connector with the user test 1. And the first page we can see is the dashboard with some information about the data space of these user, the data entity provider, for example, consumer, the offered service of this user and company, the subscription to the service, the request pending, and so on. Another interesting feature is the catalog. In the catalog, we will see all the data offering service defined in this data space with some information, the category, the user offering, the title, the data creation, the status, eventually the subscription, and the type, data or push to divide into the two category type. The service macro menu enable the item service categories of the to define the user data offering. Then we have the my offered services with the data offering that are in charge of this user. In this case, the page is divided in two tabs: the data type and the push type, to differentiate the two category of the two type of data offering. Then we have the request to see the request to this for this user, and the subscription to the other user or data offering. Always divided in two data and push. So we can start with data providing. The data exchange menu is the most important for the provider and consumer data. So we can provide the data as data provider. In this page, we have all the lists of the previous data that are provided by this user. And to create a new data, we can click on this button in the right top corner, new data. We select a title, for example, test AB data. Of course, we can enter also a description and select the file to be provided. We can select the vehicle to grid charge data with some information from the telemetry of vehicle to charge, vehicle to grid. And we have to assign this user offering, this data to a data offering. We can use an already defined service, in this case, AV data offering. In this part, we can see the information about this data offering, the title, the format provided, and other information about the category, business object, microservice. With the Save button, we can upload this data to the dataspace connector. And in this page, the data, after data is saved, we can see that as the first item of this table, the new data provided. So we can switch with the data provider user. Okay. We have another tab with the user test 2 that acts as a data consumer. Login as data consumer, then navigate to the data exchange menu and the consume data interface. The consume data interface is split always in data and push. And if we can see that the first item is the last item provided. Go in the detail of this element, and we can see the main information, title, description, and the file provided. And of course, we can download this data. So in this case, the connector of data provider user test 2 communicate with the connector of the user test 1 to download the data from the user test 1 connector. So the data is downloaded. We can save this data, and we can open also the file. This. Okay. And as you can see, we have the file with the vehicle to grid charging data. We have some information about timestamp, power, and other information regarding the vehicle to grid charge. So next, we have a nice features for the final user, the data exchanges timeline, in which we can see all the exchanged data from this user. And we have in the left sides of this interface, the data provided by this user. And on the right side, the data consumed by these users. In this case, the first item is the last data consumed, and we have also the notarization blockchain enabled, so we can check for the presence of the smart contract. So we will see a new link to the to the blockchain smart contract. Some information about the blockchain. We use in this case the Polygon blockchain, the test net of the Polygon blockchain that is called the AMOI, and we can see the explorer that show the last transaction. This with some information about the time, the complete information about time, data time, the transaction hash, and the fee and the input data that we saved in this transaction. So we use a smart contract deployed on Polygon to trace also the data exchanged. This complete the data exchange demo. The last feature that I wanted to show today is the NATS integration. We can use the graphical user interface of NATS to send any information to a test NATS server deployed in my environment, in my PC. For example, okay, NATS work with the topics. I don't know if it's clear. It's a bit low character, but in this case, we will send a message to a AV charge topic with simple information about the temperature, 20 degrees. So I send this information in the NATS topic. And in this case, the ingestion service of data space read this new message from NATS and create a new data. So this data automatically for these users, user test 1. Of course, there is a configuration that enable this, the user to be used, the link URL of the connector, and some other information. In this case, this element is created by the automatically by the NATS service, and if we want, can also download this data with the user test 2. So we have this data, EV charge topic, access to this element, and download.
Was it also showing in the timeline, Marcantonio?
Yes.
It was there. Okay.
We can download, and then we can see the timeline with the notarization service of the blockchain. So in this case, the temperature is written in a TXT file. And we have just a moment. And we have the JSON with the temperature that we sent before. If you want, we can open also the data exchange timeline, and we have the EV charge topic with the data that is uploaded automatically by NATS. We can check also the smart contract, open the link, and see the transaction in the blockchain explorer.
Very nice.
Okay, this completed this demo. I don't know if there are any question, curiosity.
Yeah, Marcantonio, thanks for this. It was very comprehensive. In fact, we we reached the point where we decided to launch this open mic discussion. If the colleagues who are still connected and had the patience to endure till the end, thank you so much. Now is the time, if you would like, either in written form or just open the mic to interact with us and pose your questions. They are very much welcome. In fact, I see that we already had one question, and also we have the other questions at the time on the last meeting that we didn't have time to respond. So I do see here a question from Tom Tansey. And he asks, how is over-the-wire security handled with NATs? Maybe to Matthias, no? The security aspect was a bit covered by you, but
I think that question was answered.
Was it? Okay.
Yes.
It's clear. Thanks, Tom, for the question. Let me see if we have other questions here. We did have some. I can retrieve them. So one was a bit clarification regarding the LPC conversion from Modbus to MQTT. What is exactly being converted, since neither Modbus or MQTT are data formats? Matthias, so maybe clarification about the structure that the IEEE 2030.5 presents, no? Here a clear distinction between the communication aspect and the data format.
Or maybe I can jump in. So first of all, if we're talking about the conversion from Modbus or MQTT into IEEE 2030.5, we need to take into account the data format that we want to have in the IEEE 2030.5 domain. Okay, so in that case, the transformation consists in linking the data that are written into a specific Modbus address, okay, to a part of the IEEE 2030.5 message. Okay, so for example, we might have a mirror metering function on IEEE 2030.5 associated with an active power. So when creating the config file in that overview that Matthias showed before, where you enter the value of this mirror metering function, you simply put a link LPC Modbus address, and then you put the Modbus address from which you will read the active power value. Similarly for the MQTT part. In MQTT, the data are stored typically in topics and subtopics. So in that case, the link is not with an address, but simply with the path, the links. So the path with topics and subtopics again, the links, the information that you want what you want to include into IEEE 2030.5. If instead you want to have a transformation that goes Modbus to MQTT, the principle is exactly the same. You link a specific Modbus address to a MQTT path, and vice versa if you want to perform the other transformation. I hope this clarifies the question.
Thanks so much, Daniel, for this. And also another question here was, can we use the IEEE 20.5 NATs without any internet connection, just on local large network, on the local network? Yeah, I think that's clear.
Yeah, that's doable. I mean, you will simply need the internet connection to to pull the Docker, but once you have it, the only connection that is needed is the connection between the, let's say, the server or whatever hardware you are running the LPC with, and the assets that you want to communicate with.
I'm just being very mindful of the time. Just a couple of more minutes. I think we have time for just one or two questions, then we close. We have here, how does one know that the semantic description of the monitoring control variables is well done with a legacy protocol conversion? Does the tool help? Yeah.
You have several options to test the conversion. So once you specify the conversion, you can do some test runs with sample input messages, and you can see the output messages on the actually on the console or in the log of the legacy protocol converter, where you can verify them. Also, the legacy protocol converter has an option to validate the IEEE 2030.5 conformity of the messages. So if you turn this on, the legacy protocol converter will notify you if the structure does not adhere to the IEEE 2030.5 schema. So with this, you can basically be sure that you are compliant and that you generate the messages as they should be formatted. Yeah.
And also, still related to NATs and legacy protocol converter, could the NAT server be applied to smart metering data? Where would the server be deployed at the device level? Would it require a dongle, or the smart meters could handle this?
Well, we had the case here in the German pilot where we were getting data from power quality meters and also smart meters, as long as any metering device can communicate either via Modbus or MQTT. You need to deploy NATs on the smart meter itself. You simply need to have to ensure that the smart meter is able to communicate again with the server or Raspberry Pi or whatever hardware where you're running your NAT server, and then you can do it. So the NAT server is detached physically from the metering device.
Yeah, thanks so much, Daniel. Well, I mean, if anyone else has any comment or question, please, we're just finishing our time, but I mean, we remain available for any interaction to share experiences with your own experiments. I thank you again. As a closing remark, I renew the invitation to everyone to join the final event. If you can, it would be our pleasure to have you attending. The project is coming close to an end. I think it has been a very successful project. The objectives were reached. We're still assessing the targets and the values of the KPIs, but it's really in a good shape with very intangible key exploitable results. And I would like to thank you again for being part of the stakeholders group, to have contributed in the very early stage to help us shape the requirements and then mature, and to be available through this communication channel, which was very useful for us. So we close for today, but we remain at your disposal. Guys, thank you so much. Have a nice day.
Thank you very much. Have a nice day.
Thank you. Bye.
Bye, have a nice
Bye.
day.
Thank you. Bye bye.
Bye, guys.
Bye.
Bye.